Good morning, one and all. Myself, Dr. N. Akshay, working as assistant professor in Department of EI at VNR VJEC. So, in today's session related to process control instrumentation course, we'll see how we can fine tune PID controllers. So, using continuous oscillation method. So, today's topic is tuning of controllers using continuous oscillation method. So, we'll see what is the significance of tuning of controllers, how we can tune the controllers using continuous oscillation method. So, before that, we'll just summarize the generalized closed loop control system block diagram. So, if we consider this particular generalized closed loop control system diagram, where our aim is to maintain output at set point in presence of disturbances also. So, we can see here, if you write the overall transfer function, say consider the input is YSP, let's say output is Y, consider disturbance is D. So we'll consider here the gains. So let's say GC is the controller gain, final control element gain is consider GF, say the process gain is GP, disturbance gain, let's say it is a GD, and the measuring device gain, consider it is a GM. So if you rewrite, or if we write the transfer function for output Y, or if you write equation for output Y also for this entire thing, so we can get the equation that is GC of S into GF of S into GP of S, this divided by 1 plus GC of S into GF of S into GP of S into measuring device gain GM of S multiply by input YSP of S. So this is the part 1 for servo mechanism or for set point tracking. For the second part, that is for the second input, that is for the disturbance, we can get the disturbance gain G of S divided by transfer function will remain same, GC of S, GF of S, GP of S, GM of S, and this multiply by disturbance variable D of S. Now if you see this equation for output Y, we can see that the output has to maintain at set point, or the effect of the disturbance has to be minimized. It mainly depends on the characteristic equation. If you see the characteristic equation elements, it consists of combined gains. There is a controller gain, final control element gain, process gain, as well as a measuring device gain. So this is the characteristic equation. But if you see the characteristic equation, what changes can be, or where changes can be made, or what values can be selected by the process engineer. So as the final control element gain is fixed, or process gain is also process gain is fixed, and measuring device gain is fixed. So user or controller gain has to be changed by the user, or we can say the operator. So if we select, now what is the significance of this GC of S? You can see that when we want the output must follow the changes in the input, or in another case when we want the output, so case 1 the output should follow changes in input, that is for the set point tracking, we can say first case. Whereas in second case, when input is constant or set point is constant, we want output should also remain constant by minimizing effect of disturbance. So it also depends on controller. So how properly we are going to select controllers here? So in this case, selection of GC, that is a controller, is very important. So what type of controller we need to choose, whether P controller or PI controller or PID controller. So this is first thing. If we are using P controller, then what should be the proportional gain value? How much should be the proportional gain as well as integral time value for PI controller, and how much should be the value of KC, TI and TD, that is the derivative time for PID controller. So the selection of controller and controller parameters is very important, because we know that if we see this time response analysis, so this is the time response analysis curve. So if you see this time response analysis curve or time response curve, we can see that with respect to time t, here the output of the system is changing. So this is the output. So if we are using different types of controllers, so we are using only, now we can say the proportional controller, right? So let's say I'm using a proportional controller with low gain, then the output may not, so in this case the output may not change, output may not reach the set point variable. Let's say output will stay here. So let's say this is with proportional gain, let's say 2. So if I'm using proportional controller with, let's say, a little bit high gain, in that case again the output will reaches uh, right, but it will not be at set point. So let's say this I'm taking something gain equal to 8. So if we use very high proportional gain, then in that case we may get oscillatory response. So proportional controller, and what should be the proportional controller value, that selection is very important. If you see the another case, let's say we are using integral controller. So if we go with the PI controller, so in that case you can see that there is a large overshoot. So because of the overshoot, the settling time is also increased one. But in this case we can say the steady state error is almost becoming 0. So if we have to make the dynamics or the response of the system faster, we are going to introduce derivative control. To minimize the error, we are adding integral gain or integral time, that is what integral action, and to track the the process variable, whether it is a reaching set point or not, or to follow the error or to track the error, we are using the proportional controller. So the time domain specifications like rise time, peak time, settling time, steady state error, as well as peak overshoot. So how we are going to get the optimum control response? So for example, we need steady state error, ideally it must be 0, peak over should be, that we should be very small, settling time should be very less, right? So peak overshoot should be also it should be shorter, or the peak time should be also a lesser one. So these all things we need to check it. So it depends on how or what type of controller we are going to use. So mainly let's say we need to check how much should be the say the settling time. It should be very lesser one, right? Then what should be the steady state error? Ideally it must be 0. Then my system must remain stable. So let's say I'm considering now these 3 parameters. Also let's say peak overshoot, it should be also very smaller one, right? So when I want these parameters should be maintained, there is nothing but small settling time, steady state error 0, smaller peak overshoot, and I need my system should remain stable. So it mainly depends on what type of controller we are using, and the most important thing, what are the controller parameters. So how to select proportional gain, how to select proportional gain and integral time Ti for PI controller, how to select Kc, Ti and derivative time, that is a proportional gain, integral time, as well as derivative time for the PID controller. So the selection of controller parameters is very crucial to maintain or to get a better response from the controller. So this selection of controller parameters plays very important role in process control instrumentation. So what is the requirement? Requirement is to select optimum values of these PID controller parameters, so that we can get the good control specifications or the responses in terms of settling time, steady state error, stability of a system, as well as a peak overshoot. So we'll see how exactly we can use continuous oscillation method to find controller parameters. So what exactly this continuous oscillation method consists of? So in this particular case, so what I'm going to do, I'm going to consider this continuous oscillation method so that we can find out Kp, Ti, Td values. So what exactly this continuous oscillation method consists of? So let's say we have this is a process, right? Now for this particular process, let's say we need to find out the controller parameters Kp, or sorry, for the proportional PI as well as for the PID controllers in terms of proportional gain, integral time as well as the derivative time. So how exactly we are going to apply this continuous oscillation method test so that we can get the optimum PID controller parameters. So in this case, what exactly we are going to do? So what exactly this continuous oscillation method is there? Basically this we are using for higher order systems. Aim is to find out proportional gain, integral time as well as derivative time for PID controller, and we are going to apply here continuous oscillation method. So basically this test is conducted in closed loop. So this is a closed loop test, right? This test is conducted. So basically this test we are going to conduct in P mode only, that is in proportional mode only. So please remember, the test is conducted in P mode. Control can be done in P, PI as well as in PID controllers. So here, as the name is continuous oscillation method, what we are going to do, we have to find out at what gain continuous oscillations are going to introduce into the system. So what we are going to do, say as we are conducting this test in only proportional mode, so we have to increase. So first we'll have a closed loop control system diagram, right? So here only we'll select initially P controller, right? We'll slowly increase proportional gain, or the gain of the controller slowly will increase until the continuous oscillations are introduced into the system. So we are going to increase the proportional gain, or we can say the controller gain, we'll use it here, which will be the good term here. So we can say we'll increase the gain of controller, right, until continuous oscillations are introduced into the system, right? So what exactly we are going to do? Let's say I'm going to consider here, right, with respect to time t, consider this is the applied set point. So we'll check what will be the output response. So let's say I will take low gain. So for the low gain, we got, let's say, this type of response from the proportional controller with low gain. Consider gain is equal to, let's say, something 4. Now we didn't get continuous oscillation, so again we'll increase the gain of a proportional controller, and let's say after some time, say some sort of response we'll get it, let's say for k equal to say 8. Still we didn't get continuous oscillation. Now slowly we'll increase the gain until we will not get the continuous oscillation. Let's say at one gain, slowly continuous oscillations are introduced into the system, and the gain at which the continuous oscillations are introduced into the system, that is called as ultimate gain. So this is the gain at which the continuous oscillations introduced into the system. So this continuous oscillation method, it is also called as a ultimate gain method, another name for this continuous oscillation test. So this is the ultimate gain. Now from the output response, we have to find out what is the ultimate period, PU. The reason to find this ultimate gain and ultimate period is that we'll be referring Ziegler-Nicholas table to calculate PID controller parameters. Now from this output we can find out, let's say between these two peaks, we are going to calculate, or we are going to find out PU. So once we have KU and PU values, right? So we know KU PU values. So these KU PU values will substitute in Ziegler-Nicholas table. So Ziegler-Nicholas table will give us PID controller setting. So this Ziegler-Nicholas table for calculation of PID controller parameters, right? That is for P, PI as well as for PID. For all three modes, we can say calculation of P/PI/PID controller parameters we can consider. So as per this, so if we consider controller mode, say it is P, then PI as well as a PID, right? we'll find out proportional gain Kc, integral time Ti, as well as the derivative time Td. So Ziegler-Nicholas have given the formulas to calculate proportional gain for proportional controller. It is 0.5 into ultimate gain Ku. So as process to process, one process, say it is a fourth order system, it will get oscillate for a lower gain. Whereas if I consider a second order system, the process may get or may give oscillatory response for a higher gain. So process to process will be getting different ultimate gains. So we can't use the same controller settings for all types of processes. So that's what we need to find out we need to do tuning of controllers. So if we are using PI controller, then this is 0.45 into ultimate gain Ku. So to calculate integral time Ti, we'll be using ultimate period Pu divided by 1.2. So from this formula, we can calculate Ti value for PI controller. For PID controller, it is 0.6 into ultimate gain Ku. To calculate Ti value for PID controller, that is integral time Pu by 2, and for derivative time, it is Pu by 8. So once we substitute Ku and Pu values in Ziegler-Nicholas table, we can find out Kc, Ti, Td parameters for a given process. Once we got these Kc, Ti, Td parameters, then we'll set, say I'm going to use PID controller. So we'll set Kc, Ti and Td values, right? I will set these values or these parameters, and what will be the values for Kc, Ti and Tds, those will be as per calculation. So what are the calculated values are there, right? Those I will use to set the controller, and then I will use this controller to control a given process. So process to process, Ku as well as Pu values will be different. Once we know the Ku, Pu values for a given process, we can substitute them in Ziegler-Nicholas table and we can find out PID controller parameters. So thank you.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.